So for the linear part of the Jacobian, we want to find JV. Now linear velocity is simply d0 to n, the derivative of that, and by applying the chain rule we can write d0 to n dot as sum over these n joints of partial d0 to n with respect to the corresponding qi multiplied by qi dot. Okay. So this tells us that the linear velocity end effector, so this is nothing but, this is just another way of writing V0n, right? That's essentially what this is. So this was on the left hand side of our equation. So V0n is some matrix times qi dots or q dot vector. So from here we can see really each column of Jacobian would be a partial derivative of d0n with respect to qi. So what is that? That is nothing but the velocity of the end effector if all other joints were not moving and the joint of interest was moving at a unit angular velocity. So let me repeat that. The ith column of the Jacobian would be partial of d0 to n with respect to partial of qi, and that represents my end effector linear velocity if all my other qi dots are 0 and just that one qi dot is equal to 1. Right? In that case, the end effector velocity will literally be that partial derivative. Right? So that's what we will take advantage of. So let me write that again. Ith column of JV is partial d0n with respect to partial qi. This means, now let me erase this. So this is V0n. Yeah, so coming back here, this means ith column of JV is the end effector velocity if all other joints are held frozen and a unit angular velocity is provided to ith joint. So this idea we will use to derive the columns of JV column by column, and here we will have again two cases. Case 1 is if the ith joint ended up being a prismatic joint. Then with the above assumption of all other joints being fixed, things become a little easier. Let's see in a second. The above assumption of all other joints fixed all other joints, so except I joint, will mean that d0 n dot would simply be r0 to I minus 1 of d dot of I with respect to I minus 1, or I think we were using the notation of d I minus 1 to I. Why is that? Because that's the only motion that is happening, and in prismatic, whatever linear velocity you get at that joint is directly being transmitted to the end effector having that same linear velocity, right? There is nothing else that is moving in between. So the rest of the chain is moving together as one rigid body because all the other joints are fixed. So it's as if I'm saying that if I'm moving one part of the rigid body and there's no rotation, it's only linear velocity. If I'm moving one part of a rigid set of links, they are all connected together and the joints are fixed, so it's behaving like a rigid body. So one end I'm moving with a certain velocity, then the other end will have the exact same velocity with no rotation, right? So that is essentially what this is saying. That helps us a little bit because it simplifies it a great deal. And this I can then write it as really di dot or di dot multiplied by r0 to I minus 1 along the ki minus 1 direction. Yes. So thus partial d0 n with respect to qi is simply r0 to I minus 1 multiplied by ki minus 1. Okay, so that's easy. Now let's go to the second case. Case 2 is when you have a prismatic joint. So here there are a couple of steps, so just bear with me. But the idea is still the same. We will keep all other joints held frozen and provide a unit angular velocity to just the ith joint. And when that happens, in the prismatic joint, what would happen is it's as if all other joints between the ith joint and the end effector, they are all frozen. So it's behaving like one big rigid body, but there is a unit angular velocity at the ith joint. So it really it becomes a rigid body rotation, right? A pure rotation is just, v is just r omega. So this distance times angular velocity. Vectorially we will do that. That's essentially what we are doing, but we will do that in a bit of math. Okay, so here let's do a couple of steps. So first we will write d0 to n as a combination of two vectors, d0 to I minus 1 plus r0 to I minus 1 multiplied by di minus 1 to or di minus 1 to n. Okay, and just to introduce a little bit of notation, you'll say let OK denote position vector d0 to k from origin O0 to origin OK. Then in this new notation, I can take this, and these are now, I can write them in terms of O's, and I can bring this to the left hand side, or I can in fact do the opposite. I can bring this to the left hand side and then rewrite this in the following manner. So I would write this as On minus OI minus 1 is equal to R0 to I minus 1 times di minus 1 to n. Okay, this we will just save for later. We will use this later on.